Hello, and welcome to section 3.3. This is on the differentiation rules, and let's get started here. So, to jump right into it, we are going to look at our first differentiation rule. Remember, differentiation refers to the process of taking a derivative. So these are going to be some rules for taking the derivative. These are the fast shortcuts that were promised a little while ago. And once we've learned these rules, we're going to be able to not abandon, but set aside that limit definition of the derivative in favor of using these faster methods. Okay, so we're going to start with the power rule. And this is actually a rule that we've kind of been dancing around for the past section or two. So for clarification there, let's look at some of the examples from section 3.2. These were ones that we did in the videos for the last section in those notes. And notice there's a little bit of a pattern that starts to form here. Okay. One of our examples, we were given the function x squared minus 1, and we used the limit definition of the derivative to, take the derivative here. And the result that came out from that was the new function f prime of x, which was 2x. Okay. And then we had another example where our function was the square root of x. We took the derivative and came up with 1 over 2 square root of x. And then we had an example 1 over x squared for our function. Took the derivative, f prime was negative 2 over x cubed. Okay, so right now you might be saying like, what, Miss Owens, what pattern are you talking about? There's nothing there. But it might help a little bit if you wrote some of these functions in terms of rational exponents. So like this radical here, square root of x, we'll write that as x to the 1/2 power instead. And then over here for 1 over 2 square root of x, we could write that as 1/2 times x to the negative 1/2 power, because that root is down in the denominator, so negative 1/2. All right. And then kind of similarly here, 1 over x squared is x to the negative 2 power. And then negative 2 over x cubed, we could say, is negative 2x to the negative 3. Squeezed it in there. And now maybe things look a little more clear. We're looking at the powers of x on these expressions. So notice in this first example here, we go from a polynomial that is degree 2, so we have x squared. When we take the derivative, it goes to x to the first power, okay? And then here we had x to the 1/2 power. And when we take the derivative, we end up with x to the negative 1/2 power. Okay. Here, x to the negative 2 power. Take the derivative, your x is now to the negative 3 power. So between all those pairings of numbers, can you see what we're doing? The power of x over on this side, the derivative side, is always 1 less than the power of x in the original function. So 2 goes to 1, 1/2 goes to negative 1/2, negative 2 goes to negative 3. You're subtracting 1 each time we take the derivative there. And that is the pattern that we're going to focus on here. This is the basis of our power rule. Okay, so the power rule is a fast way of taking derivatives where there's a power of x involved. So we're going to write it like this: d dx of x to the n power. And let's just make a little note here for notation. remember, there are multiple ways of writing derivatives. So this is using the Leibniz notation here. So remember, d dx of whatever function, d dx of f of x, means the same thing as f prime of x. Okay, they are both just referring to taking the derivative. So this d dx of x to the n power means we are taking the derivative of x to the n power. Okay, so when we do that, the result is always going to follow this pattern. It's going to be n times x to the n minus 1 power. Okay. So basically you're going to take your exponent on the original function and bring it down into the front as a coefficient, and then have x to the n minus 1 power for that new power in the derivative. So let's look at those previous section examples again. We have x squared here. The 2 comes down into the front as a coefficient, and then we lower the power from 2 to 1, x to the first. All right, the minus 1 there, we'll take a look at what happens with this in a little bit. All right, but just focusing on the power of x right now. X to the 1/2, that power 1/2 comes out front as a coefficient, 1/2. And then we subtract 1 from that original power. 1/2 minus 1 gives us this x to the negative 1/2. So nice. And then here, x to the negative 2. All right, we're going to bring that negative 2 down out front as a coefficient, and then subtract 1 from the exponent, and we have x to the negative 3. Okay, and that's the idea of the power rule. So we can do derivatives now of this type without having to go through the whole hassle and process of using the limit definition of the derivative. You don't have to do all that f of x plus h minus f of x over h thing, take the limit. We can just use this shortcut, and that is pretty sweet. So let's do a few examples with this. Some fresh examples. Okay, we are going to differentiate the expression using the power rule, and I'll give you the expressions here. So for our first one, we're going to take the derivative, d dx, of the function x to the 5th power. Okay. Now we're going to follow this pattern. We're going to bring our exponent down out front as a coefficient, so bring that 5 down. And then lower the power on x by 1. So x to the 5 minus 1, that would be 4th power. We can even write it out as 5 minus 1, so you can really see that power rule statement there. But it's going to be 5x to the 4th. And that's the derivative. That's the derivative of x to the 5th. Okay, so isn't that so much nicer? I mean, you plausibly could have done this with the limit definition. It would just take a really long time because you'd have to do like x plus h to the 5th minus x to the 5th over h, and then you'd have to take your limit as h goes to 0. And you could do it if you wanted to take the time to raise x plus h to the 5th power. That would be a lot of distribution, but ultimately it should work out, would work out. It should come out to 5x to the 4th, but there are so many opportunities for error there. It's much nicer to just use this power rule. All right. And this becomes especially nice in functions where there is no way that you would ever distribute them out and use that limit definition, like the derivative of x to the 115th power. There's no way you're going to distribute out x plus h to the 115th. It's just not happening. It is based on that same definition, but we're just going to use the power rule here. So bring down that 115 out to the front as a coefficient. And then x to the lower the power by 1, 115 minus 1. And we get 115 x to the 114th power. Okay, that's the derivative function. That's f prime of x. No limit required there. All right, let's do a few more. Take the derivative of x to the -4th. How about? All right. And this is just to show that it still does work with negative exponents. Okay, so you bring that -4 down out front as a coefficient. -4, x to the -4 minus 1. That would be -4 x to the -5th power. Okay, so this works with positive integers, negative integers, rational exponents as well, like we saw with this x to the 1/2. Okay, it works there too. It will work with decimals. It'll work with irrational numbers, like if you had x to the pi power, you could still use this rule here. So it just works. All right. Let's do a couple more here. Let's do the derivative of just plain old x. Okay, this is good to know. Notice how this would be the derivative of x to the 1st power. If we really want to see that exponent type of setup, x to the n, so we can really highlight that n value, it would be x to the 1st. So we'll bring that 1 down out front as a coefficient. And we'd have 1 x to the 1 minus 1. That's 1x to the 0. And hopefully we all know that x to the 0 is just 1. So we have 1 times 1 here. And so we get 1. The derivative of the function x is 1. All right, let me make a little note here for everyone. X to the 0 power equals 1. That's a good thing to know. And actually, we'll use that for this next example. We'll just take the derivative of 1 itself, a constant. All right. You can think of that as taking the derivative of x to the 0 power, because we just established that x to the 0 is 1. And when we bring that 0 down as a coefficient, it's 0 times whatever comes afterwards. And so in this case, you don't really think about what comes afterwards with x there. Don't think of this as like x to the -1. That has a different setup going on with it. You'll learn more about that in Calc 2. But just know that when we bring that 0 down as a coefficient, 0 times anything that would come after it is just going to be 0. 0 times anything is 0. And so we have 0 for the coefficient. Doesn't matter what we're multiplying by. The answer is just going to be 0 for that derivative. So if your function f of x just equals 1, the derivative f prime of x is going to equal 0. Okay. And that leads us to a nice result here. The fact that we're using a constant here for our function. Any constant can be thought of as taking that constant times x to the 0, okay? So it turns out that when you take the derivative of any constant, we're always going to end up getting 0 because of the way that 0 exponent coming down as the coefficient works. So that's our nice result here. Derivative of any constant. Okay. d dx of, I'll just put c generically for any constant you want. It's always going to equal 0, no matter what that constant is. This is a really good thing to know right here. Okay, so that gave us two nice rules there, ultimately. This power rule, very important for sure. All right, this guy, start memorizing that, know how to use it. And then also this derivative of any constant, that is another good one to know. So we'll look at a few properties of the derivative that incorporate this over in the next video, but get started on memorizing these rules right here.